Example 4 is unidirectional conduction in a slab with non-constant thermal conductivity. To break that down, what we have is a value of K, thermal conductivity, that's a linear function of temperature. And we have the constants that go with that expression. What the question is asking for is it's asking for a position that goes with a particular temperature. And so that is basically asking for a temperature profile. Whenever you have a question that's asking for a temperature profile, that should trigger something in your brain that says, aha, that's asking for the heat equation. In contrast, if you have something that's asking for heat flow, heat flux, heat rate, that's usually going to trigger a use of Fourier's law. So the first thing we need to do is write out the heat equation. The heat equation from our notes for no accumulation, that is to say steady state, and no generation is just given by d dx quantity k dt dx. In this instance, we are not pulling k out of those brackets because the problem states that k is a function of temperature. And so we're actually going to need to do our integrations with that in mind. This governing differential equation is homogeneous because one side is equal to 0. It's linear because temperature derivatives don't have any non-integer powers. It's second order because there's two temperature derivatives. And it's ordinary because there's no partial derivatives. So, to solve this equation, we're going to need two boundary conditions, one for each of the two orders. To solve those boundary conditions, we need to look at the specific geometry of the problem. Here's a schematic of a furnace. If you have to design one for your D2 project, you will find my schematic rather impressive. Heat's flowing from inside the furnace outside, so we'll set our coordinate axis in that direction too. It's not required, but we'll say that x equals 0 is that inner wall, and x equals 1 is where the end of the cement wall is located. So we have then two boundary conditions that are both Dirichlet boundary conditions, and that means that the value of the function has a specific value at a given value of the independent variable. And that's basically saying that the temperature equals 450 degrees or 723 Kelvin at a particular value being x equals 0. And we'll write the same for our second boundary condition, and that's at x equals 1 meter. Now that we have two boundary conditions, we can solve the heat equation because it's only a second order equation, so we only needed two boundary conditions. To do this, we're going to separate the equation and integrate it twice. In the first separation, we see that we can easily integrate, and we will not yet apply the boundary conditions, so we'll let that first integral be a constant of integration, C1. And it doesn't matter for this integration that K is a function of temperature, but we're writing that there so that we don't forget to include that in our second separation. So that's our first separation and integration. We separate the equation one more time and integrate again. As before, we return a second constant of integration, one constant of integration for each order of derivative. And the right-hand side, we need to actually include the temperature dependence of the thermal conductivity in order to compute this integral. So the expression for K of T is A times T plus B. So if we include that, we're able to quite easily integrate the expression. And we apply the first boundary condition by plugging in the value x equals 0 meters for a temperature of 723 Kelvin. And we see here that because there's a quadratic dependence of temperature in this expression, we absolutely must use units of Kelvin because those are the units that agree with thermal conductivities. In linear expressions, you can get away with using the fact that a delta T in Kelvin has the same value as a delta T in centigrade, but that clearly does not work here. Next, we apply the second boundary condition, inserting x equals 1 meter for a temperature of 298 Kelvin. And at this point, we have two equations and two unknowns. And just to emphasize here, our unknowns are C1 and C2, because A and B were actually given in the problem statement. So, to solve our two equations for two unknowns, I would just set this term to 0, and I would start by solving for C2, and you just need a calculator to compute those values, because again, A and B are given in the problem statement. So you should get that C2 equals 1,210 watts per meter. Take care to make sure that your units are correct, and one way you can check to see if you've derived a correct solution is often that you get reasonable units. Next, we'll plug in C2 into our second equation and use that to solve for C1, and we get that C1 is negative 1,410 watts per meter squared. So at this point, we have derived a particular solution for the differential equation given a non-constant thermal conductivity. Rearranging the equation to solve for x, we can write this expression in terms of all constants and the dependent and independent variables. So this is the solution we need to solve for the first part of the question, which is what is the position at which the temperature is equal to 400 Kelvin. So to solve this, we plug 400 Kelvin into the value of temperature in this expression, apply all of the constants that we have solved for or are given in the problem, and that is just a matter of using your calculator correctly. I trust you can do that. I struggle sometimes. The value that I'm coming up with is that the steam pipe is going to be at a position of 0.889 meters. Coming back to our schematic, let's think about what that means. So a position, it's about 1/10 of the way from the outer edge is where we're going to place our steam pipe. And it's going to be at 400 Kelvin, which is 127 degrees centigrade. So that might be a little bit surprising if we were expecting a linear temperature profile. When K is not a function of temperature, we do expect that linear profile, and so the temperature changes uniformly across the thickness of the cement slab. That's not what we're seeing here though, because we have a thermal conductivity that depends upon temperature, and so in this case, the temperature is dropping a little bit faster than it would for a linear temperature profile. And that's what we're going to explore in the second part of this question. To solve this problem for the case of K constant, we still have the same heat equation and the same boundary conditions, so we just have to separate this differential equation and integrate it twice, as before. The first separation and integration yields one integration constant and K dt dx. We separate this one more time and integrate again in order to solve the differential equation. This time, because K is not a function of temperature, the integration is much more simple. And we have the solution to the simplified form of heat transfer through a slab when K is not a function of temperature. You might ask, coming back to this first step, why didn't I just cancel out the K? Because if you divide both sides of the heat equation by K, you remove it and it's still 0. Yeah, absolutely, you can do that. Do you get the same answer? Yes, you do get the same answer because it's compensated for in the constants of integration, C1 and C2. So if you include a K, you'll get different values for C1 and C2 than if you cancel it out. But mathematically, you should get the same exact temperature for any given position of X, regardless of which way you solve the equation. We apply the first boundary condition, inserting 0 meters at 723 Kelvin. Then we apply the second boundary condition at 1 meter, and now we have two equations for two unknowns, C1 and C2, and we can very readily solve for C2. I calculated 723 watts per meter, and C1, negative 425 watts per meter squared. Now to answer the question, at what position does a pipe need to be 127 degrees centigrade, or T equal to 400 K? We rearrange our equation to solve for X, and then we plug in T equals 400 K into this equation, along with the known constants. And when we do that, we calculate a value of X equals 0.76 meters. And so this is the position of the steam pipe for the case where thermal conductivity is independent of temperature. To really visualize this profile, we need to expand our schematic for the cement wall to include a much more resolved length scale. So doing this for the most recent case where K is not a function of temperature, K is not a function of temperature, we get this linear profile as expected, and about a quarter of the way from the cool edge, that's the point where our temperature equals 127 degrees C. Now, from our previous solution, when K is a function of temperature, the position at which we achieved the same temperature, 127 degrees, was closer to 1/10 of the way away from the cool edge. And so these two lines are going to intersect at this point. And what we see is that actually the temperature profile in the real case is going to be a concave down parabola. And that's slightly different from the scenario that I drew up here in my sketch. And to understand why it's a concave down parabola, we have to go back and look at our first solution. So reflecting on this solution for the K as a function of T solution, what we see is that this constant C1 is negative, and so that gives us the negative coefficient, giving us a downturn parabola. So if I'd been a bit more astute in the first round, I would have noticed that. Okay, the question that we were asked was not where is the position of a pipe placed if we don't take into account thermal conductivity's dependence. The question was, what is the temperature difference that we will incur if we incorrectly place the pipe? So what that is saying is, if we put the pipe at X equals 0.76, what will the true temperature be? So what we need to do is plug this value of X into the first set of equations that we solved, because to the best of our knowledge, K does depend on temperature, and so that solution is the most accurate solution. Combining our solution for the situation where K is a function of temperature with the incorrect position that we calculated if we accidentally placed our pipe at 0.76 meters, we're now in a position where we can solve for the temperature that would rise in the pipe if we positioned it incorrectly. Plugging our X value into the equation, we arrive at this equality, and then we need to rearrange it into something that we can solve via the quadratic formula. We can rearrange our equation as such, and what we see is that this term becomes what we would normally call little a for the quadratic equation. That term becomes little b, and this whole lumped bit here becomes our c term for the quadratic equation. And then you just have to remember, what is the quadratic equation? No mean feat. It's probably been a while since you've seen it. Here we go. This is the quadratic equation, and you can quite easily solve for temperature, given that you know all of the constants. Solving, we get that the temperature is either of two values, negative 54 Kelvin or 473 Kelvin. We have to apply a little bit of physical logic here. It is not reasonable for the temperature to be negative in this region, so that gives us our answer that the temperature of the pipe, if we were to install it without taking into account the thermal conductivity and temperature dependence of cement, would be 73 degrees hotter than if we do the calculation correctly. 73 degrees of superheat is quite a lot. That could contribute to a lot of steam pressure and damage the pipe. So the effects in this instance of not incorporating the dependence of thermal conductivity on temperature are quite enormous. We should also just take a look back on our original solution here and think about how accurate it is. Yes, we've written a very fancy expression for thermal conductivity, but we just kind of assumed that wherever we stuck the pipe in the wall, it was just going to be isothermal at whatever the wall temperature is. And that's probably not a very good assumption, because as soon as you put the pipe in the wall, you change the heat transfer profile around the pipe. And in engineering set of equations, you would have to compensate for the fact that putting a pipe somewhere changes the temperature profile. I mean, the rate at which steam was flowing through the pipe would affect the temperature profile in the furnace. So that integration of equations is what you need to really be able to articulate as an engineer, and you probably don't need to be as concerned about analytically solving it, because most of this will be done computationally or numerically anyways. So that is the solution to example 4. Thanks for watching. I will see you for example 5.